Okay, in this lecture we're going to cover the first part of our section 2.4 material on the cross product. Now in the last section we had said for vectors we can define a product known as the dot product which gives us a scalar. And in this section we're going to talk about another type of product of two vectors in 3 dimensions called the cross product which will give us a vector. So let's define this cross product. So here we would say the cross product of two vectors A and B, whose components are given, is the vector defined by the following. So first let's start with the notation. The cross product of A and B will be denoted as A cross B, or this looks like A times B. And it is the vector whose first component is given by A2B3 minus A3B2, where these A and B values are the components of the vectors A and B. The second component of this vector is A3B1 minus A1B3, and the third component is A1B2 minus A2B1. So something to make note of right away about a difference between the dot product and the cross product is that the dot product of two vectors gives us a scalar. It returns a number. And the cross product of two vectors is a vector. So one essential difference between those two products, the dot product and the cross product. Now in this definition, I'll mention that for each of these components, this formula is pretty complicated and can be difficult to remember. Like which components of A and B are you supposed to multiply, and what is the order of the difference? So this definition is a little bit difficult to remember. But we can calculate the cross product of two vectors more easily by using a notation involving the determinant of a matrix. So let's introduce the idea of a determinant of a 2x2 or a 3x3 matrix and get a little practice with evaluating these determinants. And then we'll introduce another notation for the cross product of two vectors, which will make this formula much easier to remember. So we'll start by defining a determinant of order 2, or the determinant of a 2x2 matrix as follows. So first off, we have our 2x2 matrix, where the first row of this matrix is AB, and the second row is CD. So when we're saying a 2x2 matrix, we mean it has 2 rows and 2 columns. And the determinant of a matrix is denoted by writing these vertical bars around the matrix. It sort of looks like an absolute value symbol, but written around a matrix instead of just a number. And this determinant of a 2x2 matrix is defined as follows. It's given as A times D. So that is, we take the product of the entries on this diagonal, and then we subtract B times C. So we're going to take the product of the entries on that diagonal, and then we subtract B times C, the product of the entries on the off diagonal of that matrix. Now, we could extend this concept of a determinant to a determinant of order 3, or the determinant of a 3x3 matrix, which is a matrix which would have 3 rows and 3 columns. So let's consider this matrix whose first row is A1, A2, A3, second row B1, B2, B3, and third row is C1, C2, C3. So again, the determinant of a matrix is denoted by putting these vertical bars around the matrix. Again, looks sort of like an absolute value. And for the determinant of a 3x3 matrix, we're calculating it as follows. So we're going to take the first entry of our first row, which was A1. And then we're going to multiply that by the determinant of the 2 by 2 matrix that we get by deleting the column and the row that A1 lied in. That is the first row and first column of the 3 by 3 matrix we would omit, and we're left with this little 2 by 2 matrix, B2, B3, C2, C3, and we're going to take the determinant of that and multiply by that A1 entry. Now, let me clean up my work a little bit here. Our second entry, or our second part of the determinant of this 3 by 3 matrix, we're going to subtract A2. So I'm going to subtract the second entry in that first row, A2, times the 2 by 2, the determinant of the 2 by 2 matrix, B1, B3, C1, C3, which would be the 2 by 2 matrix I get by deleting the row and the column that A2 was lying in. So we can see if we delete that row and column of the 3 by 3 matrix, I'm left with this little 2 by 2 matrix, B1, B3, C1, C3, and I'm taking the determinant of that matrix, multiplying by that A2 entry. And then for the last part of our determinant formula for a 3 by 3 matrix, we will have a plus A3. So I add the last entry in that first row times the determinant of the 2 by 2 matrix, B1, B2, C1, C2, which we can see is the 2 by 2 matrix we would get by deleting the row and the column that A3 was lying in. So we have this little B1, B2, C1, C2 matrix on the end. So for a 3 by 3 matrix, we can use this definition to sort of reduce the order of the determinants I'm working with down to the determinants of these 2 by 2 matrices, which we know how to find using the definition. So to get a little practice with this, let's look at an example. In this first example, we're asked to evaluate the determinant of this 3 by 3 matrix. So using the definition of the determinant of a 3 by 3 matrix, we're going to start by taking the first entry in my first row, which was the number 1, and then I'm going to multiply by the determinant of the 2 by 2 submatrix I get by deleting the first row and first column, which would leave me with the matrix 6, 5, 1, negative 2. Then the next part of my formula, I'm supposed to subtract the second entry in the first row, which was 2, times the determinant of the 2 by 2 submatrix I get by deleting the first row and second column. That is the row and column that this entry 2 was lying in. So that would leave me with the matrix 3, 5, 0, negative 2. And then for the last part of our determinant, we add the third entry in that first row times the determinant of the 2 by 2 submatrix I get by deleting that first row, third column, which would be the matrix 3, 6, 0, 1. So now all I have left to do is evaluate the determinants of these three 2 by 2 submatrices. So for our first part, we had a 1 times. Now remember, for the determinant of a 2 by 2 matrix, we're taking the product of the diagonal entries. So here 6 times negative 2 would be negative 12. and then we subtract the product of the off diagonals, which would be 5. So we had a negative 12, subtracting the product of the off diagonals is 5. Then for our second term, we had a negative 2 times, for the determinant of this 2 by 2 matrix, we have the product of the diagonals is negative 6, and we're subtracting the product of those off diagonals, which would be 0. So we have negative 6 minus 0, and then plus 4 times, for our last matrix, we have the product of the diagonals is 3, minus the product of the off diagonals is 0. So we have 1 times negative 17, negative 2 times negative 6 would be a positive 12, and then plus 4 times 3 is another 12. So that leaves us with negative 5 plus 12, which is 7. So we have this determinant of that indicated 3 by 3 matrix. So now that we've introduced the concept of the determinant of a 2 by 2 or a 3 by 3 matrix, let's think about how we can use that determinant to define the cross product of two vectors a little more easily. So here, making use of determinants, we can define the cross product of the vectors A and B, whose components are known, as follows. So the definition that we'll use for the cross product of two vectors, A and B, is that A cross B will be the determinant of the 3 by 3 matrix, where the first row of this matrix are the standard basis vectors I, J, and K. So a little review there. Recall the standard basis vectors for space I were the vectors 1, 0, 0, J, which was 0, 1, 0, and K, which was 0, 0, 1. And recall we could write any vector in 3 dimensions in terms of these I, J, and K vectors. So our first row of this matrix will be those 3 vectors. The second row of our matrix will be the components of the first vector in our cross product. Those are the components of A, which were A1, A2, A3. And our third row will be the components of the vector B, which were B1, B2, B3. So using this cross product definition, well, let's see what we have. Expanding our determinant, let me squeeze this in up here. For this 3 by 3 matrix, we would start by taking the first row, or the first entry in the first row, which was I, times the 2 by 2 submatrix I get by deleting the first row and first column, which would be A2, A3, B2, B3. Then I would subtract the second entry in my first row, which was J, times the 2 by 2, the determinant of the 2 by 2 submatrix I get by deleting the first row and second column, which would give me A1, A3, B1, B3. And then we add the third entry in that first row, which was the vector K, times the determinant of the 2 by 2 submatrix A1, A2, B1, B2. Now, if we simplify this a bit, we have a vector whose I component, that's the first component, would be the determinant of this 2 by 2 submatrix, which would be A2, B3 minus A3, B2. That is exactly what we have for that first component. Then for our second component, we have the negative of the determinant of this 2 by 2 matrix, which would be A1, B3 minus A3, B1. But taking the negative of that, we get a positive A3, B1 minus A1, B3. So I'll mention here when we're using this cross product definition in terms of a determinant, one thing that people typically prefer to do instead of leaving this negative out in front and taking the determinant as is, they might make this a positive, and then for this little 2 by 2 submatrix, they would just take the product of the off diagonals first, that is A3, B1, and subtract A1, B3. So either way that you prefer to think about that, you can take negative j times the determinant of that 2 by 2, or you can use a plus j, and then just remember that you're taking the determinant of the 2 by 2 in the reverse order for that j component. And then for our last component, we have plus k, so the third component of my vector would be the determinant of this 2 by 2 submatrix, A1, B2 minus A2, B1, which is exactly what we have here. And where these I, j, and k are the standard basis vectors for R3. So making use of this determinant notation for the cross product, it becomes much easier to remember that formula that we introduced in the beginning of this section. So now that we have this, let's look at some examples of calculating a cross product of two vectors. So in this problem, we're given the vectors A and B, and we're asked to calculate the cross products A cross B and B cross A. So let's take a look at this. We'll start with A cross B. So using this determinant notation, we would be taking the determinant of the 3 by 3 matrix, whose first row consists of the standard basis vectors I, j, and k. The second row would consist of the components of the first vector, which was A here, in this case 1, 1, 3. And our third row consists of the components of the second vector in our cross product B, which were -2, -1, -5. So let's see what we get here. So for our I component, we would have, so for this I component, we take the determinant of this little 2 by 2 submatrix in the bottom right corner, which we could see would be 1 times -5. So -5 minus a -3 or plus 3. Then our j component, either we can take the negative of the product of these diagonal entries minus these off diagonals, or I can think about my j component as being the product of these off diagonal entries, -6, minus the product of the diagonal entries of that 2 by 2 submatrix, 1 times -5. And then for our k component, we would take the determinant of the 2 by 2 submatrix we get in this bottom left corner. That is by deleting the first row and third column. So here we would have -1 minus a -2. So simplifying a little bit, we have the vector -2, -1, and +1. So again, the cross product of two vectors, A and B, gives us a vector, whereas the dot product of two vectors, A and B, gave us a scalar. Now, in the second part of this question, we were also asked to calculate the cross product B cross A. So using our determinant notation, we're taking the determinant of the 3 by 3 matrix, whose first row consists of the standard basis vectors I, J, K. The second row would consist of the components of the first vector in our cross product, which is now B. So we have -2, -1, -5. And for A, which was 1, 1, 3, we have those elements in our third row. So again, using the definition of a determinant for a 3 by 3 matrix, the first entry, or the I component of our cross product, will be the determinant of the 2 by 2 submatrix we get from deleting the first row, first column. So here we would have a -3 minus the product of those off diagonals is -5. For our J component, I'm going to take the product of these off diagonal entries, which would be -5, and then subtract the product of the diagonal entries, -6. So here I had a -5. I'm subtracting the -6, or adding 6. Or if you prefer, you could take the product of the diagonal entries, -6, and then subtract the -5, and then take the negative of that J component. So either approach there, you'll get the same J entry, just a matter of personal preference there. And then for our K component, we would have the determinant of the 2 by 2 matrix in this last, in this bottom left of our 3 by 3 matrix, the one we would get by deleting our first row, third column, which would give us a -2 minus the -1. So simplifying, we have -3 plus 5 is 2, -5 plus 6 is 1, and -2 plus 1 is -1. So when we compare the two answers that we found here for A cross B and B cross A, we see that these two vectors are just negatives of one another. So here, I'll say note that A cross B is equal to the negative of B cross A. So these two vectors are of the same length, but they're pointing in the exact opposite directions of one another. So we could ask the question, well, does this hold in general? Is the cross product A cross B always the negative of B cross A? And it turns out that yes, that is the case. So for any three-dimensional vectors A and B, it follows that A cross B is the negative of B cross A. And this property is called the anticommutativity property of the cross product. So in this next part of our lecture, let's consider the geometric meaning of a cross product of two vectors. So how might we visualize this cross product? So the following theorem will give us a property of the cross product and help us to visualize the vector that we're calculating. So this theorem is known as the orthogonality of the cross product, which says the following. If A and B are non-zero vectors in space, that is R3, that are not scalar multiples of one another. So that is if the two vectors are not parallel to one another. Then A cross B is orthogonal to both A and B. and the direction of A cross B is determined by the right-hand rule. So let's visualize this, a little scratch work up here. So this theorem says that the cross product of two vectors, as long as they are not parallel to one another, is a vector which is orthogonal to both A and B. So let's think about the representation or the visualization of this theorem. So suppose that we have two vectors in space, A and B, and I'll draw their representation such that they have the same initial point. So this theorem says that the cross product, A cross B, would be the vector which is orthogonal to both A and B. So that is, it intersects A and B in a right angle, or the vector A is orthogonal to A cross B, and the vector B is also orthogonal to A cross B. When we talk about the direction of A cross B being determined by the right-hand rule, it's a little difficult to explain without the visual of using my hand, but we'll say the following. So the right-hand rule indicating the direction of the cross product is thought of like this. So with your right hand, imagine sticking out your index finger and your thumb into sort of an L shape, and imagine placing your index finger along the length of this vector A, and place your thumb in the direction of this vector B. So the right-hand rule says, okay, if you're using your right hand to do that, where your index finger is along A, your thumb is along B, the cross product, A cross B, would be the vector that is sticking out the back of your right hand. So on top of your right hand, you can visualize the vector A cross B is sticking out from that at a 90-degree angle. This property of the cross product of two vectors is something that will be very useful throughout this semester. We'll make use of that orthogonality property several times. So let's look at an example. Here we're asked to find a unit vector which is orthogonal to both the vectors A and B. So we'll start by finding any vector which is orthogonal to A and B, and using our new theorem, well, we know if we find the cross product of these two vectors, it will be orthogonal to A and B. And then we're asked to find a unit vector, which is orthogonal to both of those, so we're going to have to normalize that cross product that we find to make sure we have a unit vector. So let's start by calculating this cross product. A cross B is given by the determinant of the 3x3 matrix, whose first row consists of the standard basis vectors I, J, and K. Our second row would consist of the vectors, or the components of our first vector, 1, 2, 1. And our second row would consist of the components of the vector B, which were 0, 1, 3. So taking this determinant for our cross product, the ith component will be the product 2 times 3 minus, let me color code this a little bit, so 2 times 3 minus 1 times 1. So 6 minus 1 gives us an I component of 5. For our J component, I would take the product of these off diagonals, 1 times 0, which is 0, and then subtract the product of these diagonals, 1 times 3. So 0 minus 3 gives me negative 3. And then for the k component, I would take the product of 1 times 1 minus 2 times 0. So 1 minus 0 is 1. So this vector, a cross b, we know is orthogonal to both a and b. Now you could also take b cross a here. So if we just reverse the order of the cross product, let's say if we took b times a, we would get the negative of a cross b. So here we would have the vector of the same length, just pointing in the opposite direction. So this vector would be a representation of b cross a, which is just the negative of a cross b. So it's pointing in the exact opposite direction. So it doesn't matter what order we would take our cross product, we would still get a vector which is orthogonal to both a and b, regardless of the order there. Now to find a unit vector that points in the same direction as this cross product, we need to find the magnitude of this cross product. And recall the magnitude of a vector is found by taking the square root of the sum of the squares of its components. So 5 squared would be 25, plus negative 3 squared is 9, plus 1 squared would be 1. So we're left with the square root of 35. So a unit vector, u, which would be orthogonal to both a and b, could be found by taking the vector that points in the direction of a cross b and then dividing by its magnitude, or really multiplying by 1 over its magnitude. So the first component of that vector would be 5 over the square root of 35. Our second component would be negative 3 divided by the square root of 35. And our third component is 1, and then we're dividing by square root of 35. So this would be a unit vector, which is orthogonal to both a and b. Now, if you were using b cross a instead of a cross b, you would get this same vector, but pointing in the opposite direction. So you would get the components of your vector as the negative of what I found here. So let's look at another example. Here we are asked to find a vector which would be orthogonal to the plane passing through the points A, B, and C, which are given here. So let's try to visualize this. So we haven't really formally discussed planes in space yet, but intuitively, let's say that we have some plane in 3 dimensions, and it's containing these 3 points, A, B, and C. And what I'm looking for is a vector which is orthogonal to this plane. That is, a vector which is sticking out from this plane at a 90-degree angle. So one way that we could go about finding such a vector would be to consider 2 vectors which lie within this plane and then take their cross product. So for instance, if I were to work with the vector whose representation is from point A to point B, and I took the vector whose representation was from point A to point C, let's maybe call these AB and AC. If I take the cross product of those 2 vectors, I would get a vector which is orthogonal to both of these vectors. And since both of those vectors lie in the plane, I would have a vector which is orthogonal to that plane itself. So let's start by finding the 2 vectors, AB and AC. So here I'll mention 2 vectors in the plane. for the vectors A, B. So to get our components of A, B, we take the difference in the x, y, z components of our terminal and initial point. So for our first component, we've got 3 minus 1, which is 2. For the second component, we've got 5 minus 2, which is 3. And for our third component, we have 0 minus 1. And the vector AC would be 5 minus 1, which is 4. 4 minus 2 is 2. And negative 2 minus 1 is negative 3. So if we want a vector which is orthogonal to this plane, we could consider the cross product of these two vectors, AB and AC, which would be given by the determinant of the 3 by 3 matrix, whose first row consists of the standard basis vectors I, J, K. Our second row would consist of the entries of A, B, which were 2, 3, negative 1. And our third row would be the components of AC, which were 4, 2, negative 3. So let's evaluate this cross product. We would have for our I component, the product 3 and negative 3, so negative 9, minus the product of negative 1 times 2. So we would have there a negative 9 minus the negative 2, or plus 2. For our J component, we would have the product of negative 1 and 4, minus the product of 2 and negative 3. So we had a negative 4 minus a negative 6 would give us a plus 6. And then for our K component, we would have the product 2 times 2 minus 3 times 4. So that would be 4 minus 12. And simplifying a little bit, we would have the vector negative 7, 2, negative 8. So this vector would be orthogonal to both A and B, and we can see from our figure here that that vector would then be orthogonal to the plane which contains those 3 points. And this type of problem will be something of interest throughout the rest of chapter 2 and a bit later in our course as well, finding a vector that is orthogonal to some plane. So in the last part of this lecture, let's consider another property of the cross product, namely about the magnitude of this cross product. So the following theorem gives us a little bit of information about the length of this cross product vector, or its magnitude. So this theorem says if A and B are two non-zero vectors in R3, and theta is the angle between them, where theta is between 0 and pi, then the magnitude of the cross product of A and B is given by the product of the magnitudes of A and B times sine of the angle theta between those values. So this theorem gives us another way that we could try to find the angle between two vectors if we make use of their cross product. The other formula which we were making use of was the following: the fact that the dot product of two vectors is given by the product of their magnitudes times cosine theta. So here we have a similar sort of expression in terms of the cross product. If we take the magnitude of the cross product is given by the product of the magnitudes of A and B times sine of the angle between them. Now, making use of this, we can arrive at another result, which is an application of the cross product of two vectors in determining the area of a parallelogram. So let's consider the following. Let's say if we have two vectors A and B, which form the adjacent sides of a parallelogram, then the area of that parallelogram, I claim, is given by the magnitude of the cross product of A and B. So for this result, it doesn't have a very difficult proof, so we could look at the details of this. So here what we're considering is two vectors A and B in space. So let's draw their representations. Let's say we have a vector A, and we draw the representation of a vector B such that it has the same initial point as A. So if we think about the parallelogram formed by those two vectors, let's say if we were interested in finding their sum using the parallelogram law, we would have the diagonal across this parallelogram. And if we're interested in the area of this, well, let's think about how we could find it. In general, the area of a parallelogram is given as the product of its base times its height. So the way that I've drawn this here is such that the base of my parallelogram would be the length of this vector B, or its magnitude. So my base here will be the magnitude of B. And let's think about how to find our height. The height of this parallelogram, which I'll call H, is shown here. And what we were given in the previous theorem was a little bit about the magnitude of the cross product. So if I know the angle theta between these two vectors A and B, then the height of this parallelogram would be given by the magnitude of A times sine of theta. Let's see why that's true. A little scratch work down here. If we evaluate sine of this angle theta, well, sine, defined in terms of the sides of a triangle. So here I'm looking at the triangle formed here, which is a right triangle. So sine of theta would be given by the ratio of the length of the opposite side, which would be H here, or the height of my parallelogram, divided by the length of the hypotenuse, which would be the length of our vector A, or the magnitude of A. So solving for H, well, we would multiply both sides by the magnitude of A. So the height of this parallelogram is the magnitude of A times sine of theta. So substituting that into our formula for area, well, we had a base, and we're multiplying by height, which was the magnitude of A sine of theta. But now this formula is exactly what we had in the previous theorem for the magnitude of the cross product, A and B. It was the product of the magnitudes of A and B times sine of the angle between those vectors. All right. So we've established this formula for the area of a parallelogram determined by two vectors. So in this next example, let's consider the following problem. We're asked to find the area of the triangle whose vertices are A, B, and C, which are these 3 points in space. So we want the area of some triangle in space. So let's think about how we could find this. So we have points A, B, and C, not drawn in any scale here, just to illustrate the idea. If we were to consider the area of this triangle, one way that we could calculate it using this new result about the area of a parallelogram would be to consider the vectors A, B, and A, C. And we see that these two vectors would form the adjacent sides of a parallelogram, where the area of this triangle that I'm after would be half of the area of that full parallelogram. So what I can do is take the vectors A, B, and A, C and use the magnitude of their cross product to find the area of this parallelogram, and then I would have that to get the area of this triangle that I'm interested in. So let's start by finding the vectors AB and AC. So here AB would be the vector 6, 0, 0, and the vector AC would have components 8, 3, and 2. So if we consider the cross product of AB and AC, we would be looking at the determinant of this 3 by 3 matrix, whose first row is the standard basis vectors I, j, k. Our second row would be the components of our first vector, 6, 0, 0. And our third row would be the components of the second vector, 8, 3, 2. So what we have for our ith component would be 0 minus 0. For our j component, we would have 0 minus 12, or negative 12. And for our k component, we would have 18 minus 0, which is 18. Now, using our previous theorem, we know that the magnitude of this cross product would give us the area of the parallelogram, which we had sketched to the side here. So taking the magnitude of AB cross AC, we have the square root of 0 squared, which is 0, plus negative 12 squared is 144, plus 18 squared, which is 324, I believe. And so summing these values, we're left with the square root of 468, which you might be able to reduce a little bit. I'll leave it as is. And so the area of our triangle is then half of the area of that parallelogram. That is half the square root of 468. So in this lecture, we've introduced the idea of the cross product of two vectors in space. Again, the cross product of two vectors is a vector. So something to keep in mind, the dot product of two vectors is a scalar. The cross product of two vectors is a vector. So these are giving, these two different products are giving us two different types of objects altogether. And we saw that the cross product can be defined in terms of a determinant of a 3 by 3 matrix. And this cross product has some nice properties. In particular, it is orthogonal to both the vectors A and B. And its magnitude gives us the area of a parallelogram determined by two vectors, or equivalently, the area of a triangle formed by 3 points in space.